All right, let's talk about something that's, well, kind of reshaping our entire world, often without us even noticing it. I'm talking about machine learning.
Think about it. You're interacting with this stuff constantly, probably dozens of times a day. When Netflix recommends a show you actually love, that's ML. When that junk email just vanishes from your inbox, yep, that's it too. It's basically the engine running under the hood of, well, everything you do online.
But that's the real question, right? How does a machine actually learn? I mean, how does it go from just following a set of rules to making what looks like a really smart decision all on its own? It kind of feels like magic, but I promise you it's not. So that's what we're going to do today. We're going to pull back the curtain and build a model, at least conceptually, from the ground up. We'll go step by step to really get a handle on the core ideas that make all of this possible.
Okay, first things first, let's start with the absolute basics. What in the world are we even talking about when we say machine learning?
This is really the heart of it all. You see, in the old days, a programmer would have to write a million different explicit rules. If an email contains this word and that word, then it's probably spam. With machine learning, we just don't do that. Instead, we give the computer a mountain of data and say, here, you figure out the patterns. It learns from experience, kind of like we do. And man, this approach is just incredibly powerful. It's amazing at finding these tiny, hidden patterns in massive data sets. Think about a bank spotting a fraudulent credit card swipe in a split second. It's what lets your phone sort your photos, what powers those chatbots you talk to online, all sorts of stuff. These are super complex problems where trying to write rules by hand would be an absolute nightmare. Okay, so we know what it is, but now let's get into the how. How does it actually learn? Turns out, it's not just a one-size-fits-all thing. There are really three main flavors of learning, and which one you pick? Well, it all depends on the problem you're trying to solve. So let's take a classic example. Let's say you've got a giant pile of emails. You want to build something that automatically sorts to junk from the good stuff. How would you even start?
Well, you'd probably use something called supervised learning. It's exactly what it sounds like. You supervise it. You give the machine a huge data set of emails that you, a human, have already gone through and labeled. This one's spam, this one's not spam. The machine then just studies all those examples to figure out what spam looks like. The analogy here is perfect. It's like a student studying with an answer key. And usually, supervised learning is great for two main kinds of tasks. First, there's classification. That's just sorting things into buckets, like spam or not spam. Easy enough. Then there's regression, which sounds fancy, but it just means predicting a number. Like, what's the price of this house going to be? All right, let's switch gears. New problem. Imagine you've got a big database of all your customers, right? But you don't have any labels. You don't know who's who. You just want the machine to find groups for you, to find natural clusters of similar people. Now what do? See, this time, there's no answer key. We've taken away the labels. This is unsupervised learning. You just dump all the data in, purchase history, what they click on, everything, and you tell the machine, go find something interesting. Its job is to find the hidden patterns all by itself. And it might come back with these amazing groups you never even thought of, like, hey, here's a cluster of people who only buy on weekends. Okay, let's kick it up another notch. Forget about a static data set of emails or customers. This time, you have a physical robot. And you want it to learn how to walk, on its own, across some really rough terrain. You can't just show it a bunch of examples of walking. It has to learn by doing. This is where reinforcement learning comes in. Think of it like training a puppy. The robot, we call it an agent, tries something. It takes a step. If it stays up, we give it a reward, a little digital good boy. If it falls over, it gets a penalty. And it just does this over and over and over through tons of trial and error until it figures out a strategy for walking that gets it the most rewards. All right, so we've got our three main learning styles. But what's actually going on inside the machine while it's learning? What's happening under the hood? Let's crack it open and take a look. So to really get this, you need to know about two different kinds of settings that control the whole process. First, you've got model parameters. These are the internal knobs. The machine twists these itself during training. It's the knowledge it learns from the data. Then you have model hyperparameters. These are the external knobs. These are the settings that we, the humans, have to set before the training even starts, like something called the learning rate, which tells the model how big of a change to make each time it learns something new. And the whole learning strategy, when you boil it down, is this really elegant, simple loop. 1, the model is just searching for the best possible settings for those internal knobs. 2, how does it know what's best?
It tries to make its mistakes as small as possible by minimizing a cost function, which is just a fancy term for a score of how wrong the model is. And 3, once it finds the settings that give it the lowest error, boom, it locks them in. Now it's ready to make predictions on new stuff it's never seen before. But, it's not always that simple. Things can and absolutely do go wrong. Building a good model isn't just about dumping data into a machine. It's about being a detective, diagnosing problems. So let's talk about the biggest, most common trap that everyone falls into. Picture this. You spend weeks training your model. You test it on your training data, and it's getting an A+. Perfect scores. You're popping the champagne, right? But then you show it some brand new data, stuff from the real world, and it completely bombs. What on earth happened? Well, the culprit has a name, and it's called overfitting. What happened is that your model didn't actually learn the general lesson, the signal. Instead, it just memorized the training data. It memorized every little detail, every random quirk, all the noise. The student analogy is perfect here. It's like someone who memorized the answers for one specific practice exam but has no idea how to solve a new problem. The good news is there are ways to fix this. There are cures for overfitting. For one, you can make your model simpler, so it's just not powerful enough to memorize everything. Or you can just gather way more training data. The more examples it sees, the harder it is to just memorize. And finally, you can always go back and clean up your data. Get rid of mistakes and weird outliers that might be throwing the model off.
Which brings us to the final, and I would argue the most important step of all. How do we know if our model is actually good before we unleash it on the world? How do we get a truly honest grade on how well it's going to do?
The answer is something called a test set. Think of this as a small slice of your data that you lock away in a vault at the very beginning. It is never, ever looked at during training. It is the final exam, pure and simple. The score your model gets on this totally unseen data is your best, most honest guess at how it's going to perform in the real world. And this idea leads us to the single most important rule in all of machine learning. Seriously, it is a sacred vow. If you break this rule, your whole project is basically worthless. What do you think it is? Here it is. You never, ever tune your model on the test set. The second you look at the test set score and say, let me tweak this little setting to make that score go up, you've ruined it. You have contaminated your final exam. It is no longer an unbiased judge. And here's why that's so critical. By doing that, you are literally letting your model peek at the answers to the final exam. The great score you get on it is now completely meaningless. It's an optimistic lie. And when your model goes out into the real world and sees data it truly has never seen before, it's going to fall on its face.
So there you have it, from figuring out what you want to do to picking a learning style, training the model, and then finally testing it honestly. Those are the fundamentals. That's the playbook. So the real question I have for you is, now that you know the rules of the game, what problem would you solve first?